Hello and welcome to this presentation related to masses having circular motion. For circular motion we will show that we need a centripetal acceleration and associated centripetal force. However, we'll also introduce the concept of centrifugal force, a term you may have heard of from previous study. In essence, we need centripetal force for circular motion to occur, but we can analyse circular motion problems using the equal and opposite centrifugal force. So for this mass shown here, located at some radius from center of rotation here, we will show that we require a centripetal force, an inward seeking force, to maintain the circular motion. But using D'Alembert's principle we reviewed in a previous presentation, we can analyse such problems in terms of statics by assuming there's an equal and opposite centrifugal force outward. Note that this centrifugal force is termed the inertial or compensating force and considered generated from Newton's third law due to the body's inertia resisting the change in motion as the body rotates. The aim of this presentation is to make us aware of the need for centripetal force for circular motion, but also how to apply centrifugal force to sometimes aid analysis of rotating masses. It is assumed you have seen the previous presentation relating to D'Alembert's principle before reviewing this presentation. Here's a brief overview of the presentation's contents and approximate timing shown of the various topics in the square brackets. So a brief introduction that provides illustrations of circular motion commences at 4 minutes into the presentation. There is a proof of centripetal acceleration commencing approximately 5.5 minutes into the presentation. This is quite a detailed proof related to analysis commonly found in engineering textbooks. The proof ultimately derives two equations for centripetal acceleration, one in terms of angular velocity and one in terms of linear velocity. Exercise 1A uses the derived equations for centripetal acceleration and applies them to a flywheel. That's 14.5 minutes into the presentation. Exercise 2A is basically a recap of the relationship between linear and angular velocities, that's v is equal to omega r, commences 18 minutes in. Next there is a brief proof of centripetal force, which is required to induce the acceleration, starts 20 minutes in. Then we review the centrifugal, sometimes called inertial forces, and that relates to application of D'Alembert's principles we reviewed in a previous presentation. That's around 21.5 minutes into the presentation. Some centrifugal force diagramatic illustrations are shown for reference, 24.5 minutes into the presentation, and also an overview of how using D'Alembert's principle allows a dynamic situation to be analysed as a static situation. That's 28 minutes in. The presentation concludes with 3 exercises. Exercise 1F calculates the force associated with a rotating faceplate on a lathe, 33.5 minutes in. Exercise 2F calculates the forces involved with a rotating crankshaft, 41.5 minutes in. And finally, exercise 3F, this calculates the maximum velocity that a rotating mass can have given the allowable force that the cable can withstand when rotating the mass. That's 44.5 minutes into the presentation. Here's some everyday illustrations of circular motion. The person here holding an object, this mass shown here, and rotate it in a circular fashion will require an inward seeking force to cause that motion to occur. If we're analysing fairground rides, say roller coasters, aeroplane rides, again we will have to calculate centripetal forces required for the motion to occur. If we're considering motorcycles or racing cars cornering on circuits, again centripetal forces are required for the circular motion. The term centrifugal is used often within engineering and science. For example, we have centrifugal casting processes, there are centrifuge facilities For testing purposes, there are centrifugal clutches in small motorbikes or mopeds, shown here. These are masses with friction surfaces on, attached by springs. Illustrated diagrammatically here. Here's a mass. Here are the springs attached to the shaft. So as the shaft rotates, we can consider the masses to be pulled outwards by centrifugal forces, so we can analyse movement of the friction surfaces. So centripetal forces, centrifugal forces, very common terms within engineering, and hopefully this presentation will illustrate what the forces are, why we need them, and how to apply them in practice. Let's start by considering centripetal acceleration, sometimes referred to as a center-seeking acceleration. So the disk of radius r, shown here in figure 1a here, is rotating with uniform angular velocity, labelled as omega here, relative to the centre of rotation labelled O here. Point P, shown here, has a linear velocity labelled v, shown here, and this velocity's direction is perpendicular to line OP. So the velocity here is perpendicular to the line OP shown here. It's a right angle shown there. Velocity v is represented by vector OP in figure 1b. Here's figure 1b, and here's line OP representing vector v. In time delta t, point P on our diagram here will move through an angular displacement delta theta, shown here, to point Q here. Since the disk is rotating with a uniform angular velocity, the omega, the linear velocity of point Q relative to the center of rotation, O here, will also be labelled v. So that's the velocity vector shown here at Q, again labelled v. It's shown as OQ in figure 1b. Here is vector OQ, labelled v. Here's our centripetal acceleration continued. Now in figure 1b, here, vector PQ, which is shown here, represents the change in velocity delta v, labelled delta v here. And that's between points P and Q. P and Q. So considering the geometry of figure 1b, delta v is vector PQ. And from the geometry, and using basic trig, that would be twice vector OP, shown here, multiplied by the sine of a half delta theta. That's the angle shown here, half delta theta. So in other words, we're considering this right angled triangle shown here, and we're calculating this dimension here, the opposite side of the triangle. So knowing the hypotenuse, requiring to calculate the opposite side of the triangle, we're going to use the sine function, and we will double the value of this length to get the total length of delta v. If delta theta is very small, then when using radians, sine of half delta theta is approximately the same as a half delta theta. So length PQ could be written as 2 multiplied by length OP multiplied by half delta theta, and a 2.5 multiplied together to give 1. So that's OP delta theta. So delta V can be written as V delta theta, noting that vector OP, shown here, is equal to vector OQ, shown here, and that's equal to the velocity v. From our previous work, if there's a change in velocity, then there must be an acceleration, labelled a. So linear acceleration a is defined as the change in velocity, that's delta v, divided by the time taken, that's delta t. And just for background reference, I've showed a more detailed breakdown of the basic trig approach here. Again, here's figure 1b repeated. And initially the derivation just considers this right angled triangle here. From our basic trig, sine of the angle is equal to the opposite side upon the hypotenuse. So in this case, the angle is delta theta upon 2 for our triangle. The opposite side shown here would be delta v divided by 2, and the hypotenuse in this case is v, velocity. Again, for small angles in radians, then the sine delta theta upon 2 can be written as simply delta theta upon 2. Multiplying both sides by 2 here, the 2's will cancel, so we're left with delta theta is equal to delta v divided by v. And rearranging for delta v, in other words multiplying both sides by v, the change in velocity is equal to v delta theta. Centripetal acceleration continued. So repeating from the previous slide, for a change in velocity to occur, there must be an acceleration a. A is delta v divided by delta t. But from the previous slide, change in linear velocity is actually the linear velocity multiplied by the angle turn through. So we can rewrite acceleration a as a is equal to v delta theta divided by delta t. So in other words, replacing this term with this term. And from our previous angular motion work, the change in angle turn through divided by the time taken is actually angular velocity omega. So now we replace d theta dt with omega. And again, from our previous relationship, we know that linear velocity v is equal to the angular velocity omega multiplied by the radius. And from this we can now form two equations related to linear acceleration. Firstly, in terms of angular velocity omega, so now by inserting omega r for v in this equation, we find that linear velocity a is omega squared r, or linear acceleration can be expressed in terms of linear velocity v. If we note that omega is v divided by r, then a is equal to v squared upon r. Centripetal acceleration continued. What we note here is that the direction of the acceleration is from P to Q. So from P to Q, shown here. And if we consider the situation where delta theta approaches 0, so this angle in here becomes very, very small, then the angle OPQ, this angle here, OPQ, approaches 90 degrees. In other words, considering angle theta being very, very small, and essentially point Q on our circle is coincident with point P, or on top of point P, then the change in velocity would be towards centre O. Thus, bodies moving in a circular path have a centre-seeking acceleration, and that's termed the centripetal acceleration. So just recapping from the previous slide, then centripetal acceleration in terms of angular velocity omega is a is equal to omega squared r, and the centripetal acceleration expressed in terms of linear velocity v is a is equal to v squared upon r. So these two formulae are very useful when analysing motion in a circular path, as they calculate the centripetal acceleration required for the circular motion to occur. Let's now illustrate the use of these equations with numerical examples on the following slides. Let's consider exercise 1a. We're asked to determine the centripetal acceleration of a point situated on the rim of a disc, this shown here on the right hand side, having diameter of 600 millimeters if the disc is rotating at 500 rev per minute. We've also got to calculate the linear velocity of this point on the rim of the flywheel. So the point we're considering is somewhere out here, at this radius. The answers are shown in the bracket for the centripetal acceleration and also for the linear velocity at the periphery of the flywheel. The full solution is shown on the following slide. So here's exercise 1A solution. We're asked to determine the centripetal acceleration on a point situated on the rim of a disc, shown here, having a diameter of 0.6 meters. Thus the radius of the flywheel R is the diameter divided by 2, so that's 0.3 meters in this case. So R here is 0.3 meters. Given that the disc is rotating at 500 revs per minute, we need to convert that into radians per second. So our angular velocity omega is 500 rpm multiplied by 2 pi divided by 60, so that's 52.36 radians per second. The question wants us to find the centripetal acceleration at a point situated on the rim, so of course that's out here. So centripetal acceleration, labelled A here, is omega squared multiplied by r. From above we have the omega, we have the r. So in this case the centripetal acceleration at the rim of the flywheel is 822 meters per second squared. The question also wanted us to calculate the linear velocity at this point on the rim. So in other words, find this velocity here. So linear velocity v we can calculate from the formula omega multiplied by r. Inserting the values, linear velocity v at the rim of the flywheel is 15.7 meters per second. And exercise 1A solution continued. I've just shown here an alternative form for calculating linear velocity. I'm essentially still using this value from our previous calculation, but I'm inserting it into this equation, and that is centripetal acceleration A is equal to v squared divided by r. By rearranging the equation for v is the square root of a multiplied by r, inserting the values, we get the same linear velocity. So that's just an alternative calculation, just purely for reference. Exercise 2A. A go-kart has a linear velocity of 12 meters per second. We're asked to determine the angular velocity of the wheels if they have a rolling diameter of 200 millimeters. The answer is shown in the bracket here in revs per minute. I would encourage you to stop the presentation, attempt this question, but I'll show you the full solution on the following slide. Exercise 2A, here's the solution. In the question, the linear velocity of the go-kart is stated as 12 meters per second. So v is 12 meters per second. We've got to determine the angular velocity of the wheels, and we're given that the rolling diameter of a wheel is 200 millimeters. So wheel diameter is 200 millimeters, convert that immediately into meters, 0.2 meters. So the wheel radius, which is what we're interested in here, r, is a d divided by 2, so 0.1 meters. So knowing the linear velocity of the wheel, v, knowing the radius, we'll be able to calculate the angular velocity of the wheel omega. So from v is equal to omega multiplied by r, we simply rearrange for omega, which is v divided by r. Inserting the values, the angular velocity is 120 radians per second, or converting into revs per minute, the angular velocity is 1145 revs per minute. So up to now we've considered how the centripetal acceleration, this inward seeking acceleration, is required for a circular motion. Let's now consider the associated centripetal force. So point P on the rim of our rotating disc is again shown in figure 1A, repeated here for convenience. We'll now assume that point P, shown here, has a mass, m. Thus, from Newton's second law of motion, we can calculate the magnitude of the force required. So F equals to m multiplied by a. We know that a for centripetal acceleration can be written as omega squared r, or the acceleration can be written as v squared divided by r. So this centripetal force F will act on the mass and in a direction towards the center of rotation. So this force is known as the centripetal force, a center-seeking force. So clarifying the above, we have two formulae related to centripetal force. The first one stated here is in terms of angular velocity, so centripetal force is m omega squared r. And the second formula for calculating centripetal force in terms of linear velocity v, the force is equal to mv squared divided by r. So two formulae for calculating centripetal force. So up until this point of the presentation, we have only considered centripetal accelerations and centripetal forces. There's been no mention of centrifugal force. But let's now consider D'Alembert's principle and the inertial force concept. Again, I refer you to a previous presentation related to D'Alembert's principle, where we reviewed how to apply D'Alembert's principle to various linear motion problems. Here we're going to apply D'Alembert's principle to angular motion problems. So briefly recapping from the above discussion, it's been shown that on applying Newton's second law to angular motion problems, an inward seeking force is required to ensure motion. So we call that inward seeking force the centripetal force. From Newton's second law, it's F equals ma, but for circular motion, A is equal to omega squared r. So we can derive the formula summation of all the forces acting on a body equals to m omega squared r. That's Newton's second law. However, if we rearrange the above equation, in other words, we subtract m omega squared r from both sides of the equation, we'll end up with this. Summation of all the forces minus m omega squared r is now equal to 0. And that's now in the form of Newton's first law. So this latter approach, as we've outlined in the previous presentation, is an application of D'Alembert's principle, and often used by engineers in practice. However, to apply D'Alembert's principle, we're required to add the inertial force, the m omega squared r term. In circular motion problems, that's referred to as the centrifugal force, labelled CF here. That has to be included on a free body diagram. So in other words, using D'Alembert's principle, the equation becomes summation of all the forces minus the inertial force, the centrifugal force in this case, is equal to 0. So the centrifugal inertial force is assumed to resist change in rotation of rigid bodies. As mentioned before, engineers tend to adopt D'Alembert's principle when solving such problems as outlined here, because it allows a dynamic situation to be reduced to a static situation. Let's consider a few examples where centrifugal force may be considered to occur. So hammer throwers exert a centripetal force on a hammerhead by pulling on the wire, whilst effectively feeling a centrifugal force pulling outwards from the hammer on their hands. So here's the centripetal force applied by the hammer thrower on the hammerhead, and here's the centrifugal force, the outward force that can be considered exerted by the hammerhead. Again, this is D'Alembert's principle, and of course D'Alembert's principle assumes we have body fixed axes, in this case on the hammerhead. Another example is the wall of death, found at a fun fair, which rotates and the passengers are seemingly fixed against the spinning wall, as shown here in the diagram. In this case, the wall exerts a centripetal force on the passengers, ensuring circular motion, whilst the passengers can be considered to exert a centrifugal force on the wall. Here's the centripetal force applied from the wall on the body. Here's the centrifugal force that can be considered applied by the body on the wall. Again, we have body fixed axis here. Another illustration is when a train rounds a curve. Here the outer rail exerts a centripetal force on the train, producing the circular motion, whilst the train can be considered to exert a centrifugal force on the outer rail. Again, in the diagram, here's the centripetal force, which is applied by the rail on the train, and here's a centrifugal force that can be considered to be applied by the train on the rail. And again, we have body fixed axes on the train. If it aids your understanding, one way of avoiding confusion between centripetal and centrifugal force is to remember that a centripetal force is the radial force that acts on a rotated mass, whilst a centrifugal force can be thought of as the radial force which is exerted by a rotated mass. And that can be considered generated from Newton's third law, the action and reaction law. Here's an example from a previous presentation related to calculating direct stresses in various components. This was a static analysis calculating the stress in the rectangular bar shown below, where we have a tensile force applied to the bar. Here is the direct stress calc shown here, which is the force applied divided by the cross-sectional area of the member. Engineers are generally quite proficient at solving such static problems, but sometimes have difficulties in considering and analysing dynamic problems. A static problem is a balance problem, where with this particular bar, force at one end is balanced by equal and opposite force at the other end. In dynamic situations, that's not the case. The force system is unbalanced, and that's what's causing the acceleration from Newton's second law. But it would be very nice if we could actually analyse dynamic situations using statics. And that's the reason engineers often like to use D'Alembert's principle, because it changes a dynamic situation, an unbalanced situation, and it makes it into a static situation, a balanced system. So here's a few illustrations that might help in understanding how a dynamic problem can be considered as a static analysis when using D'Alembert's principle. Let's consider this problem here, where we have a mass on the end of a piece of string and it's being rotated around with circular motion, as shown here. So if we wanted to calculate the tension in the string, or the tensile stress in the string, we could apply D'Alembert's principle. This is a dynamic situation where the mass is rotating a circle, and we know by now that we must have a centripetal force acting inward to cause the circular motion. However, if we considered body fixed axes here and applied D'Alembert's principle and the inertial force, we could add the centrifugal force acting outwards. That now has given us a balanced situation where we have a force acting inwards and equal and opposite force acting outwards. So that's a static situation where we can quite easily now find the tension in the string. It's very similar analysis to the static problem we considered in a previous presentation. So this is an illustration of using D'Alembert's principle to find the tension or the tensile stress in the string, incorporating a centrifugal force and analysing the string statically. Here's another illustration of where a static analysis is being performed on a dynamic situation using D'Alembert's principle. In this particular illustration, we've got a row of turbine blades. I want to find the stress in the turbine blades. So again, we know that to rotate the blades in a circular fashion, we have to have an inward seeking force, a centripetal force. That causes the circular motion. If we have body fixed axes here, and we apply our centrifugal force, equal and opposite to centripetal force, we again have a static situation. We have tension in the blade because of the tensile forces effectively applied in our analysis. So once again, using D'Alembert's principle, we can find the stress in the blade, sometimes referred to as the centrifugal stress. Here's the wall of death illustration mentioned previously. Here's our scenario with the angular velocity of the wall of death. Here's our rotating mass, the passenger forced against the wall. So again, if we apply D'Alembert's principle here to the body using fixed body axes, we know we require a centripetal force, the inward force on the body causing the circular motion. So this is the force applied from the wall on the person to provide the rotary motion. And applying D'Alembert's principle, we have the inertial force equal and opposite centrifugal force, which can be considered from Newton's third law to be the reactive force from the person on the wall. And if we wanted to find the tensile stresses in the wall due to the tension in the wall, we can analyse this situation statically by applying the centrifugal force, and so again using D'Alembert's principle to find the stress in the wall. So again, bringing a dynamic situation, the wall is actually rotating, but analysing it statically, like a thin cylinder. Here's a brief note for reference. Always convert dimensions to meters in dynamics to avoid unit conflict. So when we've analysed static problems in the past, it hasn't really mattered whether we've used dimensions in millimeters or meters. However, when dealing with dynamics, we need to be much more careful. If we consider the centripetal or centrifugal force formula, F is equal to m omega squared r, then if our mass is in kilograms, our angular velocity is in radians per second, and our radius in meters, then the force unit will be in newtons. In other words, a kilogram meter per second squared is a newton. If, however, we have a mass unit in kilograms, the angular velocity in radians per second, but the radius in millimeters, this will not give us the force unit in newtons. I've tried to show the above in a little more detail here. We know that the force is equal to m omega squared r. We know the unit of mass m is the kilogram. Unit of angular velocity, omega, is radians per second, so that's radians squared over second squared. And the unit of the radius r is meters. Remembering that radians is dimensionless, so our unit is the kilogram meter per second squared. And as we know, that's a newton. So the unit of force is correct here. If we consider the same calculation, but this time our radius is in millimeters, then on simplifying, we do not get the unit of the newton. The newton is a kilogram meter per second squared, but this is a kilogram millimeter per second squared, so it's not the correct unit. So this time the unit is incorrect. If dimensions are not stated in meters, always convert them to meters when we're analysing problems in dynamics. Let's consider some exercises. Exercise 1F. A casting attached to a lathe faceplate has a mass of 20 kilograms, which can be considered to be concentrated at a radius of 220 millimeters. We're asked to determine the radial force acting on the faceplate when the faceplate is rotating at 90 revs per minute. Exercise 1F, here's a sketch of the faceplate, and here's the rotating mass, which is a casting of mass M. Notice the casting is attached to the faceplate by some bolts. The centre of gravity of the casting is at radius R, 220 millimeters from the centre of rotation. We've got to determine the forces acting on the faceplate. Angular velocity is 90 revs per minute. Here's a small section through the faceplate showing the mass of the casting located here. Again, here's the faceplate labelled, and the casting is attached by bolts to the faceplate. So that's the basic scenario. So I'd encourage you to start the presentation and attempt this question. The radial force acting on the faceplate is 390 newtons. The full solution is shown on the following slide. So here's exercise 1F. Here's the sketch, but now showing the forces involved. We know for the rotating mass, or the cast in this case, to move in a circular motion, we have to have a centripetal force applied, an inward seeking force. If we're assuming body fixed axes here on the casting, then we can have the inertial effect and thus the centrifugal force, which is equal and opposite to the centripetal force. If you think of the interaction between the casting, the mass, and the faceplate on the right hand side here, the bolts here must apply an inward force, the centripetal force, to cause the casting or the mass to move with circular motion. But for Newton's third law, if the bolt is applying the inward force on the casting, there must be an equal and opposite force on the faceplate, which we can consider to be the centrifugal force. So here's exercise 1F, the full solution. Extracting information from the question, we know the casting attached to the faceplate has a mass of 20 kilograms, so M is 20 kilograms. We're informed that a mass is concentrated at a radius of 220 millimeters, so my R 220 millimeters, converted to meters, 0.22 meters. And we're also informed that the faceplate is rotating at 90 revs per minute, so my omega here, 90 revolutions per minute. Notice I've converted that into radians per second, so 90 RPM multiplied by 2 pi divided by 60 is 9.42 radians per second. We know the centripetal force is m omega squared r. Inserting the values from above, the centripetal force is 390 newtons, but from Newton's third law, there's an equal and opposite force acting outwards. So the radial force on the faceplate, which we can term the centrifugal force, is also equal to 390 newtons. That's the outward force shown here applied to the faceplate. So here's exercise 1F considered in a little more detail. This is a side elevation of the faceplate shown here, and the casting shown here. As we know by now, for circular motion there must be an inward seeking force, so that's centripetal force F. That's applied to the casting from the faceplate via the attachment bolts. This provides the circular motion. However, from Newton's third law, there's an equal and opposite force F applied from the casting to the faceplate, again via the attachment bolt. This could be considered a centrifugal force, and that's shown here. So the centrifugal force is the forces on the faceplate from the casting, and that's the outward force. If we now consider exercise 1F slightly further, we can see how a static analysis is formed when we're considering D'Alembert's principle. Here's our outward radial force, F, and if we wanted to find the reactions on the bearings, which sometimes we might want to determine, where we consider taking moments about reaction R1, shown here, that will allow us to find reaction R2, and then we can summate vertical forces to find R1. So although this is a dynamic situation, the faceplate is actually rotating continuously, we can analyse it as a static situation using D'Alembert's principle and the centrifugal force acting on the faceplate. Is that force that will generate the reactions in the bearings, shown at R1 and R2. So again, a dynamic analysis using D'Alembert's principle is now being considered as a static analysis, and we apply static techniques we've used in previous lectures. Here's exercise 2. We're asked to find the force acting on the bearing, which carries a crankshaft with an out of balance mass of 100 grams at a radius of 95 millimeters and rotating at 3000 RPM. The out of balance force is shown here in the bracket. I would encourage you to stop the presentation and attempt this question, but I'll show you the full work solution on the following slide. So exercise 2F, here's the full solution. Extracting information from the question, we know the out of balance mass is 100 grams, so M is 100 grams converted into kilograms, 0.1 kilograms. We know the mass is on a radius of 95 millimeters, so R is 95 millimeters, and straight away convert that into meters, 0.095 meters. We're given the rotational speed of the crankshaft is 3000 RPM, so capital omega 3000 RPM, and then converted into lowercase omega, which is in radians per second. The calculation is 3000 RPM multiplied by 2 pi upon 60, so 314.2 radians per second is the angular velocity. So to calculate the force acts on the bearings, that will actually be the centrifugal force F, defined as m omega squared r. Now that's the outwards radial force. As always, there must be an inward seeking centripetal force to cause the out of balance mass to move with circular motion. But from Newton's third law, there will be an equal and opposite force, which we term the centrifugal force, shown here on my diagram. And that's what will have to be reacted by the bearings. Inserting the values from above, the centrifugal force is 938 newtons. And again, as shown on the right hand side here, if we wanted to calculate the reaction at the bearings, labelled here as R1 and R2, then using the centrifugal force, we can just analyse that as a beam bending problem, as we've analysed in previous lectures. So again, applying D'Alembert's principle has taken a dynamic problem, this rotating crankshaft, and made it into a static analysis problem. In exercise 3F, we're given that the safe working load that a piece of cable can withstand is 360 newtons. The cable is used to swing a mass of 750 grams in a horizontal circle at a radius of 600 millimeters. we're asked to calculate the greatest velocity that the mass can have without breaking the cable. Firstly, we've got the greatest rotational speed in RPM, and secondly, we've got the linear speed in meters per second. I would encourage you to start the presentation and attempt exercise 3F, but I will show you a hint on the following slide if you feel you require further assistance. Here's exercise 3F and a hint. All I've done here is basically extract the information from the question. So we know that the safe working load that the cable can carry is 360 newtons. Now that's effectively in this case the tension in the cable. So again, considering analysis here, we know we must have a centripetal force acting inwards to produce a circular motion. Applying D'Alembert's principle, then we have an equal and opposite centrifugal force acting out, labelled F here, is actually the 360 newtons. That's the safe working force in the cable. The question states the mass to be swung, it's 750 grams, I've converted that to kilograms here, and we have the radius of rotation, it's 600 millimeters, so R is 0.6 meters here. We've got to calculate the greatest velocity that the mass can have without breaking the cable. So I stated two equations here that are useful, the F equals m omega squared r equation, and also V is equal to omega r, the relationship between linear and angular velocity. Just thinking our process through for the moment, what do we know? We know the force in the cable, F, we know the mass, we have the radius, so we can find the angular velocity by rearranging this equation, and we can then place it into this equation, and then knowing the radius we can determine the maximum linear velocity. So that would be my suggested approach through the problem. I'll show you the full work solution on the following slide. So exercise 3F, here's the full work solution. Information extracted from the question is shown on the previous slide. Our centrifugal force equation has been transposed for omega. In other words, divide both sides by m and r, and then square root both sides. Give us this equation. And inserting the values, we find the angular velocity is 28.3 radians per second, or converted to RPM, that's 270 RPM. And from the equation V is equal to omega r, we can find the maximum linear velocity, which is 17 meters per second. For reference, here's the bibliography used to help generate the presentation, and I hope this has been of interest to you, and thank you for viewing.